Now that winter is officially over, iced coffee season has officially begun. To make iced coffee, you can either pour hot coffee over ice or place it in the refrigerator. However, one method creates a watered down mess and the other will leave you staring at the clock for ages. Thus, we created the Pour In, Pour Out, or PIPO Chiller, a small appliance that can quickly cool any hot beverage.
Using the PIPO Chiller is very simple. First of all, let's pretend the pandemic didn't happen, and let's pretend this isn't my dog's food and is instead the chiller we built in the makerspace. So if this were the chiller, you would first use it by selecting the temperature you want to chill your drink to in the very realistic touchscreen, and then grabbing your drink, pouring it in our tumbler, and placing it inside the machine, like so. After about 3 minutes, your drink would be chilled and you would just pour it out and enjoy your chilled beverage.
Normal refrigeration happens with a refrigerant and a compressor and then some sort of heat dissipator, which happens at the back. The compressor squeezes the refrigerant, which then becomes cold, and it passes this cold refrigerant all through maybe the back of your refrigerator or the top of your refrigerator. It absorbs heat from the surroundings, and then over the course of maybe a day brings down the temperature of the contents of your fridge to what you want it to be. This works, but it's very slow. So if we want to make things faster, say on the scale of like 2 minutes or 3 minutes, we can't really rely on classical refrigeration techniques. What we use is a Peltier plate. Peltier plates take advantage of the thermoelectric effect. The thermoelectric effect involves the relationship between voltage and heat in a semiconductor junction. When a DC current is passed through a PN junction, a small temperature gradient appears that is parallel to the boundary between the two semiconductors. As we place more PN junctions in series, a greater and greater temperature gradient develops and is maintained across the top and bottom of the junction. The top becomes very cold and the bottom becomes very hot. Our specific assembly's cold plate can get below 0 degrees at room temperature. If we can dissipate the heat fast enough so that the plate doesn't break, then we can take advantage of this thermoelectric effect to cool beverages. We use 3 assemblies consisting of a Peltier plate, heat sink, and then a fan blowing away heat to dissipate heat. In this way, the Peltier plate stays functional and allows for a very cold side reaching as low as -3 degrees Celsius.
The shape and flatness of the Peltier plates calls for a flat surface to ensure direct and maximum contact. For this reason, we decided to use a triangular-shaped tumbler that would have 3 heat assemblies attached at each side.
Each side would make contact with an entire cooling plate. These 3 inward-facing cooling plates and assemblies sit atop a slip ring, a low-friction rotating disc that is driven by an adjacent low-horsepower motor. When power is supplied to the cooling plates, the motor is engaged and the tumbler, along with the 3 cooling assemblies, accelerate to a rotational velocity of about 100 RPM. When the drink is ready, the spinning slows to a stop and the user can remove their drink from the PIPO Chiller.
All in all, the aluminum triangular-shaped tumbler, along with a spinning effect, allows us to chill a drink to any desired temperature in seconds when combined with the other aspects of our device. A main benefit of aluminum is thermal conductivity. This plays a major role in the efficiency of our chiller due to its ability to transfer heat effectively.
The whole system is controlled by a Raspberry Pi. After the user selects the desired temperature of their drink on the chiller's touchscreen, the Pi will begin the cooling process. The cooling plates draw almost 60 watts of power, so the Pi enables or disables solid-state relays to allow power to the cooling plates. If left alone, the plates could reach a temperature as low as -3 degrees Celsius, which would compromise the system. Thus, the Pi uses temperature sensors to monitor the plates. Once they reach a temperature of about 2 degrees, the Pi uses what we refer to as a bang-bang algorithm to continually turn the plate's power on and off so that the plates stay at 2 degrees. Once the plates reach that equilibrium, the Pi starts an internal timer and continues spinning and chilling the beverage until it reaches the desired temperature. To calculate the time that it needs to do this for, the Pi uses a mixture of experimental data and the initial temperature of the beverage, which it estimates at the beginning. We then used Python to stimulate a boiling cup of coffee and our chiller and found that it cooled the beverage in about 170 seconds, which is something no refrigerator could do.